Right. Over the weekend, I did post a video about where I just spent the whole time going over the Chapter 9 problem sets that I just recently added to Blackboard because I thought, you know what, we probably could stand some more practice with all these different problems. So if you remember up here in Chapter 9, the first chapter that we did for this course, there's two problems here, chapter 9 problem set and chapter 9 problem set number 2. And then what I did was during the video, I went through and wrote out all the answers. And so these two sets of notes that you're seeing here, one of them is docx, one of them is PDF. They're the same thing. The reason why I do PDF as well as docx is because what can happen is with all this handwriting, very occasionally, it can get garbled if you're switching back and forth between platforms, between a PC, let's say, and a Mac, or vice versa. So if you're trying to read the docx version and it doesn't look right, there's something wrong with it. The PDF should be fine. Okay, so that's why I like to try that approach. It might look strange that they're both sitting in there together, but that's the reason why. So I'm looking through here and I see it looks pretty good. That's good. I've had problems in the past with the handwriting on this tablet where somehow it just gets all moved around and it doesn't make any sense and then it doesn't show up sometimes, or it didn't when I try to PDF it. And in the past I've had all kinds of issues, but I think it's working well now. And now today, what I'm going to do is carry on and do the problem sets in 10, which is where we started, of course, looking at hypothesis testing about two populations. And so I'm going to open those up right now and go over them with you. And if there's time, there's also a sample midterm that I'd like to go over. It's meant to be like a overview of both chapters so that we can get ready for the midterm, which I'm still working on that. I'm getting it set up so that we can have it in there and count properly. If I stick it in there now, just the way it is, it's going to affect the way it calculates your averages, and we don't want that. Okay, so it shouldn't be more than another day or so. All right. So let me get them both open. Oh, here it is. Okay. All right, let's download this one. And let's get started. All right. Now, by the way, you might want to do these on your calculator, but if you want, you can also do these in Excel. But just to be on the safe side, I'm going to show you how to do all these with the calculator because under normal conditions, we'd have our exams in the classroom and you wouldn't be allowed to use Excel. So it's good to know how to use this guy too. All right, so let's look at number one and let's find out what we're supposed to do. All right, so I'm going to copy this. All right, so we have a department store that wishes to determine if the customers from New York City tend to spend more than the customers from the suburbs. A sample of 20 New York City residents is chosen. The mean spending at the store each year is $425 with a standard deviation of 143. And by the way, even though it doesn't, that's meant to indicate the sample standard deviation. If it's the population version, it has to explicitly say so because there's no way of knowing unless you're told that, because normally all the data we have is sample data. So the way it's written here, it's understood. I hope that this is meant to be the sample standard deviation. So that means we're using the t-distribution. And we have 25 suburban residents chosen. Again, we have a sample mean, 375, a sample standard deviation, 75. We're going to test the hypothesis that the mean spending is equal between the two populations at the 5% level of significance. Now, if you notice, it says in here the population standard deviations are not equal. This is an important detail if you're trying to do this in Excel, because it has a couple of different choices. Actually, you know what? Where's my Excel? Hold on. If you look in the data analysis tool pack, now I know that some of you were having trouble with the data analysis tool pack. Now, if you look at this, um, this is really bizarre. I noticed that it's supposed to be in the data ribbon or tab, and I see that it's missing, unless this is it right here. Yeah, that's strange. It normally is labeled differently. I don't know what happened there. But as far as comparing two population means, you've got the paired sample, which is a different case. We will get to one of those examples in a bit, where the two samples are related to each other. But here, if you notice, they make a distinction between two samples with and without equal variances. And I seem to remember that the slides did not really discuss this. They assume that they're unequal to each other. But there is a case where they are equal to each other, and it does affect the calculations. But I've not put any cases like that, if I remember correctly, into the exam. So, but it's important to know that um, we, with two populations like this that we're comparing to each other, it's possible. I mean, there's two cases that we need to be aware of, one with equal variances and one without. And if you're using your calculator for this, it will ask you which one you mean. Okay, so here we're going to assume, which is normally the case, that the two populations have different standard deviations, which is usually the default assumption. But later on, I think we have one in here where that's actually not true, and I want you to see what happens when they are equal to each other. Just for your own knowledge, even if this doesn't show up in the test. So first things first, we gather up all the data. We can arbitrarily choose New York City customers to be the first population and the suburban customers to be the second. It doesn't make any difference which is which. And then we can go in here and get the data we need. Let's say, what do we need to know? New York City, the sample size is 20. The mean spending is 425. And the standard deviation is 143. In the suburbs, we chose a sample of 25. And you notice that they don't have to be equal to each other. X2 bar, this mean in the suburbs, is 375. And the standard deviation is 75. Now, they want to know, their testing hypothesis, the mean spending is equal between the two, which implies a two-tailed test. Let me just see something. Oh, I apologize. It doesn't say that at all, does it? No, you know what? There's a mistake in this problem. It starts out by saying that they want to know if the customers tend to spend more. And then down here it says we want to find out if they're equal. So that's the part that's not correct. Oh, I better fix this. I'm going to make a note to myself right now to fix this. All right. No, it looks like the intention here was that this should be a right tail test because New York City is the population. We're trying to find out if New York City customers spend more than the suburban customers. So, oops, sorry about that. This was supposed to be a right tail test. Alpha is listed here as 0.05 right there. Now, what is the test statistic in a case like this? All right, well, if you go into the slides, in fact, I think I'll open them up so we can look this up ourselves. Just as a quick reminder, we did this a while back. And so let's run through these and find what we're looking for, okay? So imagine yourself saying, I really don't remember which one it is. Um, let's go back into the slides as soon as they open up. Okay, that's if they ever open, hold on. I don't know what just happened. Oh, wait a minute. I got the wrong thing here. It didn't download the slides at all, did it? Here we go. Here we go. So we're comparing two population means to each other. And see here, they're just making a distinction between the sigmas are known or they're not. Well, here they're not. There it is. Oh, sorry, that's the wrong one. Sigma 1 and 2 are known. So that's how you know this is wrong because the Z would be used only when sigma is known. So instead, it must be this one. Going to base this on the T distribution. Uh, is this the one with the night? Yes, it is. The nightmarish formula for degrees of freedom. Um, yeah, so the test statistic here, no, that's a confidence interval. Here it is. Here it is. All right, so let's copy this into the notes. And plug the numbers in. Now, by the way, D0, remember what this is. This is the hypothesized difference between the two. And in this case, that would be 0. Okay, so we only have to plug in the rest of these. So what do we have? Um, let's split the screen so we can see what we're doing. Right, so you got to be very, very careful with this one. The difference between the means, we don't have to worry about this, the D0, it's just zero. See, the thing is, you got to watch out for these because of the way they're worded. Sometimes they give you the sample variance and sometimes they give you the sample standard deviation. So um, if they were giving us the sample variance, make sure you don't square it again. It would be easy to do that. But here, no, they're giving us the sample standard deviation. We square that and divide by n1. Over here, it's the same for 2. And whatever that is our test statistic. So it's kind of a mess, but we can handle it. All right, let's see what that's equal to. Oh my God. So for something like this, you might want to consider doing it in two stages. I think that's what I'll do right now because we don't want to waste too much time with mistakes. Um, I've got it's about 1.42. Now for the critical value. By the way, you do need to know the degrees of freedom, whether using the critical value approach or the p-value approach. This is a two-tailed test. No, sorry, it's a right-tailed test. I'm going to put DF here for degrees of freedom. Normally we write n minus 1 there, but here we're not going to do that. So the degrees of freedom formula here it's in the slides. Now, if you notice, they rounded it down. Not every book does it that way. I guess we'll stick with that approach because the calculators are perfectly capable of doing this. Now, again, just to save time, I know we can figure this out for ourselves, but I'll just tell you that it's 27.24, which will round down to 27. I'm sure you can do this on your own, but for something like this, there's no point in spending all night with it. So how do we look this up? Second vars, number 4 is our old friend INVT. And remember, this one requires the left tail area. So you're going to ask for, or tell it, area. 0.95. And degrees of freedom, we're going to call it 27. Actually, I think the reason why that rounding is happening is because they don't want to assume that you're using a calculator. If you're using a table, it would have to be an integer. The calculators are capable of finding the t statistic when we have a fractional number of degrees of freedom. But we'll just follow along what they're doing. And let's see where this takes us. We're getting about 1.703. All right, so now we'll compare that with the test statistic. Okay, there's our rejection region. And the test statistic was about 1.42. So let's put that in the graph. So that means clearly we do not reject the null. Which was that mu1 minus mu2 is less than or equal to 0. So in other words, they were trying to find out if it's, people in the city are spending more. But that's not the case, okay? Now, I mean, imagine they were planning on doing some big promotional effort in the city, if that was true, if people were spending more, but that none of that will be needed now because we're seeing that there's no evidence that they're spending more in the city. Now, what about the p-value? All right, well, the test statistic is where we determine that from. So here, it's a right-tailed test. So anything above that, here's our test statistic. Consider the p-value. This whole area is the p-value. To find this, we need to calculate the probability that t is greater than or equal to 1.42. And how do we do that? We use second vars. Number 6 is TCDF. All right. Now, this one requires us to tell it the lower limit, the upper limit, and the degrees of freedom, which we know is 27. So we try that. And we get 0.0835. So remembering that the alpha is 0.05, and that of course means do not reject the null. Excellent. All right. Now in the test, in MindTap, I mean, I don't think it's going to require you to do it both ways. It'll almost certainly just ask for one or the other. And even then, sometimes it'll just ask you, what is the p-value? Or it might say, what is the test statistic? So you may not even have to go through the whole hypothesis test. All right, so what's next? I don't know what happened. I guess problem set one has disappeared. Here it is. All right, so what's going on here? We have research being conducted to determine if the average number of miles driven each year by men is equal to the average for women. Okay, so this one really is meant to be a two-tailed test. They want to find out are they equal or not? In other words, this would be of interest to an insurance company who's got to decide how much of a premium to charge to their men and their male and female customers. So let's write that out. So first, the mean, the null is that the means are equal. Oh, sorry. No, in this book, see, again, every book is different. They're writing it like this. Alpha is 0.05, I think. Oh, no, sorry, it's 0.10. I should have read it first. Now, this is the data that we have. And again, it doesn't matter which population is one and which is two, as long as you're consistent. For the men, we have 100 in the sample. The average number of miles is 11,800. Oh, wait a minute. Sorry, I jumped ahead a little bit. The men are 100 in the sample size. The average number of miles is 11,200. And the standard deviation is 844. Over here on the women's side, the mean is 11,800, and the standard deviation is 743. Um, so, uh, you know what I'm noticing here? I guess I'm gonna have to really update this thing. It looks like in my answers, it looks like the intention was for these two standard deviations to be the population standard deviation, but I don't see it there. Um, I must have really been rushing through this. I was trying to get these ready, and I guess there is a couple of screw ups. So, in other words, this thing is very badly written because it should say a population. So I'll post a corrected version of this tonight or tomorrow. Just to say, God, population. Now, the reason for having it like this is because this time we'll be using the normal distribution. So I wanted you to see both cases, T and normal. Okay, so we'll fix these. Um, okay. Now, I don't think this case showed up in the slides. We didn't have any examples of this. Every one of these cases used the T, but it's good to know that this case exists. If by chance these are population standard deviations, then you're going to use a slightly different test statistic. Everything's the same except that, yeah, it's just population standard deviations. The calculations are the same. This is 0. The important difference is that the critical values will be chosen from the standard normal instead of the t. That's really the main difference. All right, so let's figure out our test statistic. All right, beautiful. Okay, so if you pop that into your calculator, and again, I'm going to do this in 2 stages. It just reduces the risk of a mistake by about 1,000%. 115, 14. It's approximately negative 5.21. Now that's a big number under the standard normal distribution. So it looks like we're going to be rejecting this null hypothesis. But of course, let's go out of our way to figure out what the critical value is, or R, because there's two of them. So if I remember correctly, the alpha is 0.10 in this case, which is unusual. So that's our rejection region. And now let's randomly pick this one to look up in the calculator. All right, so when you get to INV norm, um, the area is the left tail area, 0.05. And of course, the mean and standard deviation are 0, 1, because this is the standard normal distribution. And you'll come up with negative 1.645. So that means this one is negative 1.645. This is positive. All right, so But our test statistic is so far out here. This is not drawn to scale by any means. Um, we're way out there on the left. So clearly we reject the null and accept the alternative that they're different. Now, we don't know what the insurance company is going to do with this information, but chances are it just means that that's one more factor that will cause the premiums of the women drivers to be different than the male drivers. Okay. Because, these guys, these insurance companies, they have armies of statisticians to help them figure out what to charge, the appropriate premium to charge for insurance of all kinds. And they take into account dozens and dozens of factors, and they understand how each one contributes to the likelihood of costing them money, okay, or filing a claim. So it's a very complex area of study, but it has to be done. Otherwise, insurance companies couldn't survive if they couldn't do this. But all right, anyway, what about that old p-value? Well, what you need, because it's a two-tailed test, principle sum of these two tails. Now, each one of these by itself is going to be really, really small, like scientific notation small. So you'll see. So let's just double the right tail. So we go to second vars, number two normal CDF, because that's where we calculate probabilities. And of course, this one, if you recall, asks for lower and upper. $521 up to infinity, which of course is replaced with second comma 99. The mean and standard deviation are 0 and 1. And if you try that, you'll see that it's preposterously small. It's ooh, I didn't realize it was this small. Yeah, that means 7 leading zeros. And so 2 times that isn't much bigger. God, look at this. Anyway, so as far as we're concerned, in fact, if this was a printout on a package like Excel or a specific, a very dedicated software package meant for just statistics, it would just show zero. They wouldn't bother to show all these digits. They would just say it's zero. Let it go. So clearly that means we of course reject the null. And accept the alternative that they're just not equal to each other. Okay. Now, this next question, I think we're going to skip over it. I'll tell you why, because this is the case that's not in our slides. Um, what they're assuming here, if you notice at the end, This requires a somewhat different test statistic, which apparently the book isn't using. So I think we're just going to skip over this one. Okay, I think to avoid confusing you, we'll just because you're not going to see it in the test anyway, and you're not going to see it in the MindTap assignments. So therefore, we'll skip number three. We're going to move on to the second of these two problem sets, which are the matched pairs cases. And you remember doing these, I think. You've got, like here, for example, a new drug is being tested to determine if it lowers cholesterol. A sample of 8 volunteers is chosen. The cholesterol readings of the volunteers before taking the drug and after are shown in the following table. And so the difference means this reading minus this reading is here. So this is the one where we don't really need to know the individual values. We just need the differences. And that makes it a lot easier to conduct our hypothesis test. You also remember that we're able to do this with our lists, okay? Because the test statistic is a little unusual compared to what we've done. So let me remind you what it looks like. All right. Let me just make sure it's clear. This is what we have up here is, yeah, I'll make a note here. All right. And they're both the same type of problem. All right, let's go back to the slides. Now, this is 10B, by the way. Oh, no, it's not. Sorry, my mistake. It was at the end of 10A. So remember, we use slightly different notation. That little d means difference. So let's copy this question here. Okay. Now, here's what we have to ask ourselves. Given the way the differences are calculated, this is a cholesterol drug. Do we want the readings to go down or up? So if that happens, then this difference was going to become positive or more positive. So we're going to find out whether the drug is working by testing this as a right-tailed test. Although it sounds backwards, we want the readings to go down, but it's a right-tailed test because the way the difference is defined, a lower mean for the second population means that this goes up. The difference is positive. That is very confusing to a lot of people. And everyone, really, the first time you do this kind of stuff. So we have alpha is 0.05. Now, what are they having us do about the test statistic? Now, we can do this if we want to. But I showed you a way to avoid doing this in the lists, and I think we should stick with it. Unless you really want to do this, you can certainly feel free. But if we to use lists, you're going to put before in list one, after in list two, and then we're going to create our own column. I'll remind you how to do that. Okay. It's because this is all that we really need. So we can then use this to actually calculate the test statistic with substitution, and then we can compare it to the critical value. So this way you don't have to calculate SD all by yourself or D bar by yourself. Okay. So let's see, what numbers do we have? Oh, what happened? I'll tell you, let me just copy these. So what you're going to do is type these. Remember how that works. You go to second. Oh, actually, sorry, you do not do that. You go to stat. Then when you get there, you're already in the right place. Edit, one edit. And then you're at the lists. You should ideally clear out all the existing lists. Go to header with the arrow key. And that'll take care of it. Then you type, okay? Go ahead and type. Now, I'll tell you what, since the difference is already there, you don't really even have to bother. I did, well, it's already in the problem. You don't need the first two lists. You can just type the differences if you want to. But remember, if you don't, there's a way you can enter a formula for list three that does the calculations for you. Okay, so, but since the difference is already here, you probably should put the differences in maybe list one and then run with it there. Okay, so since the differences are given, we will enter them into list one. Why not? All right, let's do that right now. Here they are. 5, 5, -1, 7, 3, -3, 7, and 4. When that's done, you can go back to stats. And this time we'll choose a different menu, which is calc for calculate. All right. Stat. But this time go to the middle menu, Calc. And then the one you want is number one var stats. Enter. Now make sure it knows where you've put your list of differences. If it doesn't already say L1, you can enter it by typing second one. That will give you the L1. And then scroll down. You can skip over frequency list. Don't pay any attention to it. Calculate. Now, you'll have all this wonderful information in front of you. What do we do with it? Well, let me remind you what we need. What you're seeing here listed as X bar is what this formula is seeing as D bar. Mu D is 0. That's the hypothesized difference. SD is what the calculator is calling SX, which is approximately 3.6228. And then N, of course, is 8. There's 8 observations. That's going to give us our T statistic. All right. It's approximately 2.63. So what about the critical value? Now remember, this is a right-tailed test. Let's go back and show you that again. And so our critical value will be now, since we only have one sample of data, meaning the differences, this one is a very easy formula for degrees of freedom. Just like what we saw in chapter 9, n minus 1 is our degrees of freedom. And there are 8 volunteers, so we have n minus 1 is 7. Look at number 4, INVT, in the second VARS menu. And right, so that means the left tail area is 0.95. And the degrees of freedom is 7. All right, let's see what we get. About 1.89. Remember, just a second ago, we calculated our test statistic to be 263. And so that, of course, means that we reject the null. And by the way, that means that the new drug is working because it lowers, we have hard evidence that the mean is lower, which means that the drug is lowering our cholesterol. Now, of course, for the p-value, we want anything green than the test statistic. Actually, let me draw that again. I want to reinforce how skinny this tail is. So we're looking for the probability that t is greater than or equal to 263. We go to second vars, 6 T CDF. All right, here we go. Now this one requires a lower limit. To freedom is 7. All right. It's about 0.0165. Actually 695.6. It's, well, whatever it is, it's clearly less than alpha. So that means that the p-value just means we reject the null and accept the alternative. It's positive, which again means that the drug is working. So now the second one is kind of the same thing. I guess I should have made it different, but um, this is what we're looking at for the second question. Um, let's see, what do we have here? So now here we're advertising some. We're trying to find out if the average spending per household on a specific product has increased after a major advertising campaign. Now here we want the spending to increase. This is actually reversed from the first one. So mu d, which is mu1 minus mu2, if the spending rises, this will be negative. So it's, again, it's hard to imagine, but this is actually a left-tailed test. That would mean that after the advertising campaign, the spending goes up. It's a 1% level of significance. The test statistic is the same as before. Except that it's D bar instead of X bar. So guess what we have to do? We have to type these differences into one of our lists. It doesn't have to be list one. If you want to keep the other data, you can put it in list two. But either way, we have to enter this into a list. So we enter the data into a list, specifically the differences, and use stat calc stats. And what you're going to get, again, oh, and make sure it knows what list you want. I just assume you put it back in L1. And you'll get all the data you need. It should be SD down there. So here I'm seeing 2.108. Here we got 4.48. 35, let's say, over square root of 6. And let's see what that turns out to be. Let's see. Yep, 1.15. Now, that's a very small value for the t statistic. The chances are we're not going to reject this null. Okay. So the critical value, the left-tailed test. But also remember, alpha is 0.01. Oops. So there's 6 observations. So we have 5 degrees of freedom. And so, of course, we go to our calculator and look for second vars for area, 101. Degrees of freedom is 5. And that will give us Negative 3.36. Our test statistic is up here somewhere. Yeah, that's right. Anyway, what this shows us is that we do not reject the null. And that's it. So that means that this, by the way, this was meant to be this was about a diet pill. And then the p-value would be absurdly large. So for that, we need to go to second vars, 6. Okay. Or second comma 99. Upper is 115. And degrees of freedom is 5. This is going to be, yeah, 0.848. Come on. So that's obviously whatever alpha is 0.1. And that should take care of that. Oh, there's one more here. There's one with proportion. So that's good. We haven't done this yet. Um, we need some practice with two proportions. Let's see what that's all about. So a researcher wishes to determine if the proportion of retirees is the same among men and women. Cal test. So what do we know? 80 men, 90 women. 5 men are retired. 8 women are retired. Oh, wait, sorry, that's it. I got it backwards. It's X over N. So 5 out of 80 is approximately 0.0625. Side of the fence. We have 0.0889. Now, for this one, the test statistic is, let's see. Oh, yeah, it's this one. Actually, I'll tell you what, let's go back to 10B and show you where to find this. That's for the confidence intervals. Here we go. Okay, now you can see, boy, that's a lot of calculations. All those bars, all those P bars. This is P bar right here. So what do we have here? 81 bar is 0.0625. So this is a weighted average of the two. It's going to be approximately 0.0765. So that means we can now come up here and do this one. Let's get it out of here. All right. Well, it's kind of a mess, but let's see what we can do. So again, the numerator, I think we should do them separately. Point oh 0408. Ratio works out to be about negative 0.6 0.47, let's say. Now, again, that's a very small value. For the normal distribution, we're not going to reject the null. Let's find the critical value anyway, because that's not how stats works, is it? No, you've got to be very precise. So, it was a two-tailed test. So alpha was 0.05. Yeah. Okay, so we can look up, let's say this one. So INV norm, and so we need the area, which will be that left tail of 0.025, mean 0, standard deviation 1, and that leaves us with negative 196. All right. But of course, we just got through showing that the test statistic is really small. What is it? Negative 0.647. Wow, that is small. So clearly we do not reject the null. That the proportions are equal to each other. And that just simply means that the proportion of men and women who are retired, there's no evidence to show that it's different, okay? All right, and let's see. Oh my God, the p-value is going to be through the roof. It's a two-tailed test. We need two tails. So we'll figure out this one first, and then we'll double it. That means Um, what are we looking for? Negative infinity up to negative 0.67. Oh, what did I do? No, I'm sorry. It's not 67. 647. I just copied it wrong. Oh, sorry. I'm looking at the wrong tail. It's everything from negative infinity up to negative 0.647. Let's calculate this. Point 2588, but we have to double that, remember? So the actual p-value is two times that, or, adding them together. 0.5176, which is well above alpha, so we do not reject the null. Wow, that was a lot of reviewing. Now, there's also this sample midterm, but I'll tell you what, maybe let's do this. Why don't we start chapter 14 and we'll get to this tomorrow. I don't know. I think we've done a lot of reviewing for one night. Um, just because it would be more interesting, I think if we start something new right now. The sample midterm will be very similar to what you're seeing here anyway. So here's what we'll do. We'll finish or go over tomorrow. Tonight, then we can at least take a peek at chapter 14, which is regression analysis. Now, regression analysis is used heavily. Any discipline that does empirical research, meaning that you're using real world data to try to draw conclusions, chances are you're going to use regression analysis because it's very powerful and very flexible. It gives you the ability to do a lot of things, but there's a basic framework that we need to understand. Now, of course, the calculations themselves are very, very complicated. And so we're going to lean on both Excel and our calculators to get our results. It's getting to that point where doing this by hand or focusing our attention on the calculations no longer makes a whole lot of sense. We're getting into the territory where we really want to spend more time analyzing the results. And so the deeper you get into statistics, the less time you spend doing actual calculations and the more time you spend analyzing the results. You can let the computer do the hardcore grinding. Your job is to understand what it means. So let me get this thing open. Chapter 14. Yes, it does have its own spreadsheets. But you'll be really surprised how much Excel is capable of doing here when we get to this. Now, by the way, there's another chapter in the book. Chapter 15 is called Multiple Regression Analysis, which is the next step up from what we're doing here. It's the more advanced version. And if you find that you might need this stuff for, let's say, research project you're working on or for one of your other classes, just be aware that chapter 15 goes over multiple regression if you're interested in it. For us, this is where it stops. The course ends at chapter 14. But because all the material is there, I mean, if you really need it, you may as well go use it. It's it's more complicated, of course, but you never know when you might need it. But here we're going to stick with just the basics, what's called simple linear regression. The bottom line with this is that we're trying to estimate the equation of a straight line, which doesn't sound like a huge challenge. Oh, but how wrong you would be if you said that. So now the reason why this is so challenging is because you're not in the real world, the relationship between two variables is never perfect. Okay. What we're trying to do is come up with a sense of how strong and is the direction between two variables. In fact, we need to know the strength and direction of the relationship between two variables. So, like, what would be a good example of this? Suppose that, oh, you watch TV enough. You see that in this day and age, there's a ton of commercials for insurance companies. That seems to be all the rage. There's one in particular, you've probably seen it, where there's this guy, I guess he's a therapist, and he's helping treat young homeowners who are turning into their parents. I'm sure you've seen the ads. You recognize them as soon as you see them. So the question is Progressive convinced that these ads are increasing their sales? They must be. Otherwise, why would they spend so much money in them? So, but it would be nice to know the exact relationship between the dollars spent on advertising and the increase in sales that result from that. And that's the kind of thing we can analyze with regression analysis. So, let's let this be our first example. Progressive wants to know, and boy, they spend a fortune on advertising. If their advertising on TV is generating enough revenues to pay for the commercials or to pay for the advertising. Okay. So, how would they do this? So the company gathers up their data on their expenditures, revenues over the past, let's say, 20 years. And this way, they want to look at the data and get a sense of what it's telling them. Now, one good way to organize this data is to show it in what's called a scatter plot. And so the way that works is this. We assume, let's make a note of this here. We assume that sales revenues depend on advertising spending and not the other way around. So that means X, which is our independent variable, is advertising, and Y, the dependent variable, is the resulting cells. I guess that makes sense to everyone. It's not the other way around. The advertising drives the cells. It's not the other way around. So if you were to plot this data, scatter plot, each point represents 1 year's worth of data. Like here, for example, could be 2020, where X is we assume that these are both measured in millions of dollars, let's say. And let's say at that point, 2035, meaning that that year they spent $20 million in advertising and their sales were 35 million. And then maybe this year, 2018, they spent only $16 million in advertising. Their sales were 44. And so there's going to be points scattered all over the graph. And in this case, because neither variable can be negative, we can just focus our attention on the first quadrant. And you're going to get a bunch of points. Now, based on the way I've drawn the dots, it should be clear that there's a tendency as X increases, means that we move to the right. There's also a tendency for Y to increase. How can you tell? Because look at these points. They're heading in, let's call it a northeasterly direction. And if I were to draw a line through these points that gets as close as possible to all of them, trend line, and I'll show you how to do that, by the way. The slope is positive. It means that there's a direct relationship between X and Y, meaning they both either go up or down at the same time. So we know that in general, years in which we advertise more than usual, we also tend to have higher sales revenues and vice versa. That's really what this means. Now, I'll tell you what's missing though, and this is the part we're going to include, or we're going to learn how to do this too. Trend line can also tell us by how much sales increase as a result of an increase. Actually, what I should say, well, all right, let's leave it like this. Sales increase as a result of an increase in advertising. It means, of course, and how much sales decrease as a result of a decrease in advertising. So in other words, like imagine if I wanted to know If I spend 1 million more dollars on advertising, how many millions of dollars will my sales go up? That's an important number. And we can derive that with regression analysis. Okay. The scatter plot is fine as far as it goes, but we're going to create an actual equation which shows us how much every dollar of advertising is affecting our sales. And that's how we can decide, should we continue advertising or not? So, in other words, if every dollar of advertising only increases your sales by 75 cents, well, then you have a problem. But if it's increasing your sales by $2, then you might as well carry on. But of course, that depends on whether the commercials are good or not. I mean, obviously, some places do produce some nice commercials. They're very interesting. People are paying attention to them, and others not so much. I'm sure you've seen ads on TV that were so bad that you decided not to buy that product as a result. That you do get that. But here, it's very professionally done. It makes you want, I mean, even if you don't buy the insurance, at least you know who they are. And that's the important thing. Your name is everywhere. All right. Anyway, so this is where we're going. What we're going to do is see how to estimate this trend line and then how to interpret it. But we're going to do more than that. We're also going to run tests on this line to make sure that the results make statistical sense. Okay, because the reality is you could put any data on that scatter plot and there'll be a trend line of some kind. And it doesn't necessarily mean that it's telling us something important. So we have to distinguish between meaningful results and results that don't really mean a whole lot. So, all right. So, by the way, that means there will be some hypothesis testing and confidence intervals coming our way. We are going to only use, if I remember correctly, the T distribution in this chapter. No, I'm sorry. We're also going to use the F. Okay. So I think that's it. But we know how those work anyway. All right. So why don't we take a peek? Oh, by the way, we'll see later on that the data analysis toolpack can help us with this too. We're going to see multiple ways of getting our results with the calculator as well as with Excel. One or two of the ways do not involve the data analysis toolpack, and one or two of them do. Okay. All right. Now, by the way, there's many different ways to do or carry out regression analysis. We're doing a specific type. It's called the least squares method, and you'll see why it's called that when we get there. But just be aware there are other ways of approaching regression. Ultimately, it depends on what kind of data you have and what assumptions you're willing to live with. Because like all other techniques we've been learning, there's a lot of assumptions being made here. And here, like I may have mentioned before, specifically, we're assuming that some of the variables that we're dealing with are normally distributed. So managerial decisions are often based on the relationship between two more variables, like the decision to continue advertising on TV. Regression analysis can be used to develop an equation showing how the variables are related, specifically a linear equation, meaning the equation of a straight line. And when we do that, it's really the slope that we're interested in. The intercept is not that important. It's really the slope this is all about. Okay. Now, yes, the y variable is sometimes called the dependent variable. The x is the independent variable, meaning that y depends on x, not the other way around. And yeah, and they mentioned that down here on the bottom. Very good. Simple linear regression means there's only one dependent and one independent variable. What else could there be? Well, you'll see in 15 if you decide to read it on your own. Studies the relationship in a single independent variable and a dependent variable. Or is you're studying something like this. And what would that say about multiple regression? Which again, we'll not be doing here. Studies the relationship and a dependent variable. So let's say, for example, let's say progressive thinks that their cells depend not just on advertising, although they think that it does. So advertising, and let's say they're also pretty convinced that it depends on GDP growth. So this is what we mean by multiple regression because you've got three. We could think of this as X1, X2, and X3 instead of just the one independent variable. Now, unfortunately, while this is very powerful, it's a lot more complicated. And that's why they've had to save it for chapter 15. The math gets, but again, this is why at this stage, we're starting to lean on packages. We're not going to do this stuff by hand. So sadly, that has to be saved for a later chapter. Now, I don't know if this is something you'd be thinking about, but if you've got some electives available in your program, in the economics department, what we're doing here is a branch of statistics. Um, we use something called econometrics. Basically, economic statistics. It's with a fancy name. Every discipline has its own specialized features. They need certain parts of statistics and they don't really need the rest. So this a class in econometrics would be very different than, let's say, biostatistics or psychological statistics or something like that. But what I'm getting at here is that this is where you would find out what multiple regression is all about. So they do offer this in the economics department. I think it's only for seniors, but still they do have it. So one day you wake up and say, I must pursue this further, you would have to go to the economics department and get probably permission to take this as an elective. But that's what it would be. It would be like what comes after this. So Like the thing is about statistics, it's a very useful tool, but you always find occasionally people where this is so exciting to them that this is what they want to specialize in. Okay. In fact, I had a professor at Fordham with exactly the same thing. He taught econometrics, and this was his whole life. This was it. This is what he cared about. But if not, that's okay. What we're doing here is plenty for you, but it's there if you want it. Okay. Um, very advanced, but it's very powerful. It would be useful, like for people who are doing research of some kind. All right. Anyway, back to this. Now you can see already it's starting to get scary. Look at this. So, what is this that you're looking at? This is called the population regression line. This is the line that would result if you had all the data in your population instead of a sample. Okay, now if you notice the Greek letters, remember I mentioned this a few times. The convention in statistics is that Greek letters are reserved typically for population measures, such as, some of them, mu, sigma squared, sigma, whereas the Roman alphabet, the one that we use, are meant for sample measures. Which would be things like S bar, S squared, S. So the fact that we have Greek, by the way, what is this letter here? The fancy B is the Greek letter beta. It corresponds to the B in the Roman alphabet. So that's how we know this is some kind of population line or measure because of the betas. We're going to estimate the sample version of this, of course. Oh, by the way, there's another one hiding in there too. This is the Greek letter epsilon. It's cloaked with mystery, but um, usually it's used to represent something that's uncertain. And so what I'd like to do is show you how these lines are similar up to a point. This regression line of an intercept. What is this doing here? Well, I'll tell it to you first, and then we'll explain it as we go along. This is known as an error term. What is it doing there? All right, well, let's take a step back here. Actually, let me do it like this. So let's say you probably remember This is the relationship between Celsius and Fahrenheit. It's a straight line. Intercept is 32, and the slope is 9/5. So given this, no matter what Celsius temperature I give you, then let's say F would be 50 degrees Fahrenheit. All right. So in other words, like let's say that point is here. Now, here, this is a very precise relationship. There's we sometimes call this a deterministic relationship. Because knowing the temperature in Celsius exactly defines for us the temperature in Fahrenheit. It's not the case that we can say, well, it's going to be around 50. It is exactly 50 because that's how it's defined. Okay, so all the points are on this line, and they tell us this how this relationship works. So there's others here too. But on the right, let's say we're dealing with sales and advertising. This is not a precise relationship. The points are not all directly on the line. Why? Because other factors besides advertising affect the sales. So this is known as a probabilistic relationship. Because we don't know the exact, if we, let's say we have this regression line and we say, well, if we advertise $50 million less next year, what will be the resulting sales? Well, you can't say with any real exact, precise certitude. You can just come up with an estimate, an interval, let's say. So that being the case, let's just focus on 1 year's data. Let's say this is the regression line here. Distance between that point and the line is the error term. For a given x, this is x1 and y1. Here is what was wrong. Or actually, what I should say is our actual value is different from what was predicted. Oh God, what was that? All right, anyway, error term simply means the actual value of y for a given x. Um, so now with this kind of data, we need to capture that. Um, Whereas up here, we don't. There's no point in having an error term because there aren't going to be any. Okay, if we did, they'd all be zeros because the relationship between the two is deterministic, meaning that the value of C uniquely characterizes the value of F. There's no discrepancies. Here, the relationship between sales and advertising doesn't work that way. There could be other factors in here that we're not capturing. And let's face it, this is based on human behavior, which can change at a moment's notice. So this relationship is not as precise. So the error terms are there to capture how far away we are from the actual predicted values. Now, those error terms are actually very helpful indicators of how good a job we did with our regression line. They can give us a lot of insights into the data that we have and whether or not our assumptions are correct. We're not going to get to this just yet. Maybe later we'll look at a graph of error terms and you'll get a sense of what this is helping us decide. It helps us decide if the regression line makes sense or not, basically. Like I said, remember, it's understood when we run these regression lines that there really is a relationship between X and Y. If I chose two variables that weren't really related to each other, then the error terms would be enormous. They'd be all over the place, okay? If the relationship is very strong, then the error terms would be very close to zero. All right, so we'll get into all of this as we go along. Right now, think of this as sort of a coming attraction as to where we're going with this. Okay, so now the betas are the word parameter means a population measure. The opposite of that, as you may recall, is a statistic, which is a sample measure, like over here, such as mu. And the corresponding one here would be X bar. When you see that word parameter, it means you're talking about a population measure. That's all it means. A statistic means a sample measure. And because these are Greek letters, what they're referring to is this equation. Yeah, which we don't know, but we will estimate them from our data. And of course, error, that's our error term. Now, they do make an interesting point here. We'll get back to this in a bit, but epsilon is a random variable, which we introduced way back in stats 1. And that implies that epsilon follows a probability distribution happens to be normal. And it has what are called moments. They're summary measures of a random variable. Like what? You say, expected value variance. I'll put these in the same line to remind ourselves that they're related to each other. They're not really two separate independent moments. So epsilon is a random variable, own probability distribution, which happens to be normal. It also has its own formulas for expected value variance and standard deviation. Get back to this soon. Now, the equation is written like this. What is that supposed to mean? Well, same thing. Because the expected value of epsilon is 0. And that's another way of saying its average is 0. Sometimes it's positive and sometimes it's negative. They cancel each other out on average. Okay, so while, yeah, there's error terms all over the place, some of them are positive, some are negative. On average, they add up to 0. That's what this means. If they don't, then there's something wrong. Okay. So, in other words, so how does that explain what this notation means? Well, if you look at the error terms, on average, they'll be 0. And so the actual population regression line is defined without errors. In other words, the expected value on 0 plus beta 1x. So that line is what the relationship would look like without any error terms. What we're going to do is estimate these two terms. We're going to figure out the value of the intercept and the slope from our historical data. And then we can come up with a model that lets us determine relationship between these two. And so we'll be able to use it to make predictions. Like, for example, I want to know what y would be for a given level of x. In the case of Progresso, I might say if I'm going to advertise $20 million next year, on average, how should the sales be? That's what this is for. And what, by the way, what that implies here And again, I don't wait on this line, center of a probability distribution, which is allowing for scatter all around the line. Each of these points on average is on the line, but there's room for it to spread around. But that's what this is telling us. Curves has the same value, mean and standard deviation. And there are tests that we can run to make sure this is true. There's so many tests that we can use with regression analysis. Ultimately, most of them depend on the assumption of normality. Okay, what else? Here it is. Instead of having y be the expected value of y here, and this is our regression line, population that is. The intercept is beta 0, and the slope. Now, of course, there's other possibilities. Here's a negative relationship. The slope is negative. Here it's 0. This means that there actually is no relationship between x and y. It's like, imagine if Progressive suddenly discovered that people are not buying the insurance because of the commercials. They don't care about that. They're buying the insurance, and you realize, wait, we're wasting our money. Nobody's buying it because of the ads. So why are we doing this? This is what the relationship would look like in that case. Okay. That's how we know that the two variables are not related to each other, don't influence each other. Oh my God. This is starting to seem, all right, let me just show you briefly what's coming next. Obviously, we're not going to be able to estimate the population regression line. Instead, we're going to estimate the sample regression line. And it looks like this, okay? So this is where the bulk of our attention will be focused. Oh, sorry, not simple, sample. So the way this works is that pointy thing. Sample value of y. Um, this is the estimated value beta of beta 0 and beta 1, as opposed to the population where we know them both. So if you notice that there's no error term, on average, so it drops out of the regression equation. What page is this? 10. All right. So I think we had enough for one night. So here's what we'll do. Tomorrow we'll run through this sample midterm just to get more practice for the exam. And I'm not sure how long that's going to take. Then we can get back to this. Yeah, that should do it. It'll be a good night. This way we don't spend the whole night just reviewing, reviewing, reviewing. It's nice to have a mixture of both in the same class. So anyway, so now all of this looks really terrifying. At first, it does look that way, but once we start doing it, you'll realize it's really not that bad. Okay, there's new terminology to learn, but it's deceiving to say the least. How terrifying it looks because there's a lot of new notation we need, new terms, new concepts, but it won't be too bad. All right. So we'll pick it up tomorrow right here. Oh, not right here. First we'll do the sample midterm and then we'll get to this part again and take it from there. Okay. And also I just want to point out this is the last chapter in the book. So I don't know what happened. I find that I tend to go faster when we're online for some reason. So if you looked at the assignments, you'll see that we're pretty far ahead of where we need to be to finish this class. Oh, yeah. In other words, the sample midterm is just for practice. We're going to work at it together. The real thing is going to be embedded in MindTap as soon as I figure out how to do it, which will probably be the next day or so. And so that will be the actual test, the one in MindTap. This is just for practice. Now, I also want to point out, because we're doing this online, normally the actual test that I give you would be similar to the sample midterm, but because it's being done online with the MindTap, it's actually all multiple choice, although you do have to do a lot of calculations on your own. So the format of the actual test will not really be like this because they can only really ask you one thing at a time. Okay, so in other words, it's going to be very much like the MindTap assignments you've done up to this point, more so than the problems you're seeing here. So imagine it's almost like a more high-powered MindTap assignment. I don't know if that's good news or bad news, but that's the basic structure. Okay. All right. Anything else? Good. I hope you're not too blown away by all this. No, it looks, like I said, it looks scarier than it really is. So once we get used to it, you'll see that it's not too bad. All right, and we'll see how important it is, why it's so useful for research. So, but yes, anyways, I started to say we're somehow got pretty far ahead of where we needed to be, which is not the worst thing in the world. Better than being behind, that's for sure. I think the last day of this class is like August 7th, which is, oh, that's got to be at least 3 weeks from now. Roughly 3 weeks, or more or less. So anyway, so time is not going to be a problem. Let's put it that way. Okay. All right. Anyway, so I guess I'll just see you all tomorrow night then.
Thank you.
All right. Good night.
Thank
Thank
you.
you.
All right. Bye.
Thank you. Thank you.
Bye.
Thank you.
Night.